Alright, Peter Neal here. I'm doing the reporting for the gas turbine experiment we did last week. Just a little overview. I'm going to go over that testing apparatus, background and theory, procedure, data analysis, and calculations, guys. It's a lot, so just bear with me on that. And conclusions of the basic idea of the experiment. The apparatus that we have here, what is a gas turbine? Basically, it is used for jet engines, mostly commercial aircraft over long distances. What we'll have is a diffuser linked to a compressor, linked to a combustion chamber, followed by a turbine, and then finally followed by a conversion nozzle all in series. Basically what happens is our gas, our air, will be sucked in and compressed in our compressor radially. Once it is, the high pressure gas is then led into the combustion chamber. It will be combined with our fuel, was butane for this experiment. Then that will fire and combust, leading through and then finally exiting out of the velocity out of the converging nozzle exhaust. The exhaust gases will come out producing our thrust, which is what we're looking for. But just a little TS diagram. The main idea here is just from 1 to 2 for the compressor and 3 to 4 for the turbine. Ideally, we want isotropic. All of you know that that is possible. So the closest that can be 1 and 2 isotropic, the more efficient our system will be. Procedure, it's labeled on the glass above the apparatus, but anyway, basically we just turned our throttle on, powered it up, and let some time for the fuel to ignite. Once it did, it fired. From there, we could throttle adjust it to whatever RPM we wanted to measure. And from a recorder standpoint, the data we wanted to gather was pressure, temperature, fuel mass, flow rate, and thrust data. Each of these points will be taken at different RPMs. We actually didn't, we were supposed to do 10, but we actually got 9 from 40,000 to 80,000 RPM. Also, we were given data from a factory model, but I'll talk more about that later. Also note that there's a thrust rod that was mounted to the bottom of the apparatus, which would also link to the stand. That measures the thrust force that was outputting from our turbine engine. Here's what gets interesting. Okay, our mass flow rate of the air. Again, here, see, I have a second plot. I call it theoretical, but it's basically our factory model of the gas turbine engine. It's still good. It was only given at around 52,000 RPM, so it's not as many data points, but it's still good to be able to compare that. So basically what we were given, we knew the density and the energy released, as well as the energy from our fuel. Therefore, we could find our Q. Then manipulating this equation, we could solve for mass flow rate of the air. As you can see, our experimental model was higher. For thrust, we use this formula. Again, note that this formula is a Bernoulli equation. It's actually more accurate than the thrust equation that we used here, the V equals thrust over mass flow rate. I just thought that the experiment was pushing us to use that equation because we were given thrust and we just saw for mass flow rate, so that's what I did. Again here, this is supposed to be 0 because it starts at 5,200 RPM. Also, I'm off 1 decimal place on my y-axis. This is supposed to be 200, 400, 600, etc. As you can see, the theoretical or the factory model is higher for that. The fraction percentage of fuel burned in each component for our compressor, as you can see for our experimental, it was almost 100% or all of it, but not quite, because some of that fuel was burned in the turbine as well. For our theoretical, it's much lower. We also use these equations to find our fuel percentage also. Next one. And if you go here, as you can see, I have a negative value for our experimental. That is because the temperature 5 was actually less than the temperature 4 at each operating point, which are our temperatures. That temperature should be less because it has more time to bond and heat transfer with the environment, rather than 4 when it's coming closer out of the combustion chamber. It's going to be hotter. T3 is actually our hottest temperature, so that's right after the fuel combusts. But as you can see, so we have this percentage, and for the theoretical, the previous slide, you can see that fuel consumption, along with this, doesn't add up to 1. That's because the other fuel is from the theoretical or factory model was burned in the turbine, actually. So, just combining our work with our compressor and our turbine, I use this equation as well. I got negative values for our compressor because T2 is greater than T1. For the turbine, we got our highest work because temperature 3 was our highest value of temperature in the whole system, because obviously that was right after the compressor. That's right after the gas compressor is going to be hottest. Isentropic efficiency, I graphed that using our entropy equation, our temperature entropy, and our delta temperature as well. Note that this only applies to the compressor because the turbine actually has fuel burning inside of it. So you would need to add a heat addition item, and that would kind of throw off the work and everything. So I did it over the compressor. And although there's a dip there, as you can see, generally the efficiency increases with RPM. And just some conclusions I made. Again, Bernoulli's principle, using the pressures and densities, is more accurate than the thrust over velocity or mass flow rate equation, but I use the other one. So, also, generally, efficiency is increased with RPM. I think that was the main idea of the whole experiment and conclusion I came to. Any questions?